All right, welcome everyone to this plenary panel of reliability of autonomous machines. Reliability is a key requirement for autonomous machines, although the commercialization of autonomous machines is thriving in recent years. A systematic understanding of the reliability problems in autonomous machines is still missing. In this panel, we invite top experts from industry and academia to discuss autonomous machine reliability issues from different perspectives. Let me briefly introduce our panelists today. First, we have Professor Cecilia Metra. She is a full professor at the University of Bologna, Italy. Professor Metra has been a member of the IEEE Computer Society Board of Governors since 2013 and of the IEEE Council on Electronic Design Automation Board of Governors since 2015. Professor Metra has served as the 2021 IEEE Division 5 Director-elect and 2019 IEEE Computer Society President. In addition, she's on the IEEE the Institute Advisory Board as well as on editorial boards of several journals, including IEEE Design and Test, Journal of Electronic Testing, and Design Automation for Embedded Systems. Her research has received public and private funding from companies such as Intel Corporation, STM, Microelectronics, etc., at national and international level. Her involvement with industry was also recognized by a joint patent with Philips Research. She has received 2 Meritorious Service Awards and 5 certificates of appreciation from the IEEE Computer Society. Professor Metra is an IEEE Fellow, IEEE CS Golden Core member, and a member of the IEEE Honor Society, IEEE HKN. So welcome, Professor Metra. All right, next we have Professor Yuhao Zhu. He is an assistant professor in the computer science department and an affiliated faculty in the Georgian Institute for Data Science at University of Rochester. He graduated from the University of Texas at Austin and previously held visiting researcher positions at ARM Research and Harvard University. His current research interests are application, algorithms, and systems for visual computing, as well as safe computing systems in the AI era. Welcome, Yuhao. So next, we have Dr. Bo Yu. He received a BS degree in Electronic Technology and Science from Tianjin University, China in 2006, and PhD from the Institute of Microelectronics, Tsinghua University, Beijing, China in 2012. He's currently the CTO of Perception, a company focusing on providing visual perception solutions for robotics and autonomous driving. His current research interests include algorithm and systems for robotics and autonomous vehicles. Dr. Yu is a founding member of the IEEE Special Technical Community on Autonomous Driving. He is a senior member of IEEE. Welcome, Dr. Yu. Last but not least, Zishen Wang. He is a PhD student at Georgia Tech, advised by Professor Arvijit at the Integrated Circuit and Systems Research Lab. He has general research interest in VLSI, computer architecture, and edge intelligence, with a special focus on designing efficient and reliable computing for autonomous systems. Before coming to Georgia Tech, he received the MS in electrical engineering from Harvard University, advised by Professor Vijay Reddy at the Edge Computing Lab, and collaborated with Professor David Brooks and Professor Guyong Wei at VLSI Arch Lab. He received the bachelor degrees in electrical engineering from Harbin Institute of Technology in 2018. So welcome everyone. So first, Professor Metra will give a talk regarding the importance of reliability in autonomous machine computing. So I will hand over the stage to Professor Metra.
Thank you very much, Dr. Liu, for your kind introduction. So I will share my screen in a second. And so I'm very glad and honored to be part of this COMPSAC 2022 panel. So as we all know, autonomous machines are increasingly adopted in a widespread variety of application scenarios. And we can see here autonomous drones, autonomous vehicles used for space exploration, autonomous robots used in the industrial production environment and elderly care robots. So the expectations are that the autonomous vehicle market will have a compound annual growth rate of the 21% by 2024. And we have seen several autonomous vehicles that have been employed also to face the pandemic emergency. So on the picture on the left side, we see an autonomous vehicle that has been used in Florida in order to move some COVID-19 tests from a drive-through testing site to a processing laboratory. While on the picture on the right, we see an autonomous vehicle that has been used in China to deliver food and medical supplies to infected areas and so on. If we now think about the field of autonomous mobile robots, also for them, the market is expected to have a significant compound annual growth rate by 2024, and particularly of the 20%. We have assisted to the use of autonomous mobile robots also to face the pandemic emergency, to disinfect infected areas and to help medical personnel. And but in these particular cases, these autonomous vehicles and autonomous robots were moving on predefined areas with minimal interaction, if maybe no interaction with humans, and minimal interaction with the environment. But if we now think about highly autonomous machines capable of autonomously interacting with the environment and humans, of course, we understand that they should be highly reliable, highly safe, highly available, and highly secure. Where, as we all know, by definition, reliability is the ability to guarantee the continuous delivery of the intended, so correct service for a given amount of time. Safety is the ability to guarantee the absence of catastrophic consequences on environment and users. Availability is the ability to provide the intended correct service when it is needed. And security is the ability to protect data from unauthorized access, corruption, and misuse. So, of course, these are requirements for our highly autonomous intelligent machines, but what does it mean in detail? So if we think about high reliability for these highly autonomous intelligent machines, I think that we would need to guarantee the autonomous machine correct operation despite possible faults or aging conditions that might affect the hardware in the field. Of course, all of this holds true also for the software, but we will hear about the software in the following presentation, so we'll focus on hardware. So we should guarantee the reliability of the hardware with respect to any faults, just like they could be transient faults due to energetic particles hitting the silicon or aging conditions that might affect our hardware in the field. If we think about safety, I think that we will need to guarantee that the autonomous machine is able to put itself in a fully autonomous way in a safe state in case of hazardous conditions. Because, for instance, if we think about a level 3 autonomous vehicle, in case of hazardous conditions, an alarm message can be generated and the driver may be required to take control. But if we think about a fully autonomous vehicle, level 5, this can no longer happen because the driver may no longer be present into the vehicle. So in case of hazardous conditions, it should be the autonomous vehicle itself that should be able, for instance, if the hazardous condition happens while being on a highway, it should be able to slow down the speed, move to an emergency lane, and then reach a parking lot and then stop the car. Because as we all know, the safest condition is the condition where the machine is doing nothing, so it is stopped. And so we should guarantee that the hardware demanded to move, as well as the software, of course, to move the autonomous machine into a safe state is correctly working, so is highly reliable. So we can see that the safety requirements mandate also the high reliability of at least the hardware that is demanded to move the system into a safe state. And concerning availability, of course, we will need to guarantee that the machine is functional, because as we just mentioned, the safest state is a state where the machine is doing nothing, but of course, we would like our, for instance, autonomous vehicle to be also operational. And concerning security, we need to guarantee that if, for instance, some additional hardware is adopted in order to guarantee the security of the data, this hardware is correctly operating in the field, despite the possible occurrence of faults and aging conditions. So again, we would have reliability needs for the hardware demanded, possibly present and demanded to guarantee data security. So this to show that I believe that reliability is a global constraint for highly autonomous machines that needs to be satisfied not only in itself and at the global machine level, but also at the machine's hardware component level in order to meet the machine requirements not only of reliability, but also safety, availability, and security. So if you want our autonomous machine to be reliable, safe, available, and secure, also to guarantee the safety, availability, and security, we need, at least for the hardware blocks that are demanded to meet these requirements, we need to have high reliability. And in particular, so this applies, for instance, to hardware accelerators that are implementing the AI that, as we know, is massively adopted in autonomous machine in order to enable them to take their autonomous decisions, as well as to other blocks that may be adopted to reach a safe state in case of hazardous conditions or to guarantee data security and so on. And for all these hardware components, reliability should be guaranteed with respect to all possible faults that might occur in the field, as we just mentioned, transient faults, bridging faults, and so on, and also aging conditions that, again, may occur in the field. So let's see some examples of possible problems. For instance, we verify that if soft errors affect the memory elements of other accelerators used to implement deep neural networks, for instance, for image recognition on an autonomous vehicle, if the memory elements affected by soft errors are those containing the weight, and in particular the exponent of the weight the weight. So what could happen is that we could have a possible misclassification of images included in the training data set. So images of objects for which the DNN has been trained may be erroneously recognized. Or another possible problem is that the DNN could fail in recognize an out of distribution image, so an image from an object for which the DNN has not been trained. As a result, in both cases, we could have erroneous identification of an image for this autonomous vehicle, and so consequently the action taken by the autonomous vehicle may be not the one that we would like, and of course, this would imply a risk for the safety of our system. So we can see how in this case, the presence of, the limited reliability, for instance, of the hardware accelerators implementing neural networks for image recognition could compromise the safety of the whole system. Let's see another example, instead related to security. So we verified, and this analysis and this research has been presented in a paper that is currently under review, that if soft errors affect memory elements of hardware accelerators implementing autoencoders, that, as we know, are a particular kind of neural networks used to detect the presence of unauthorized messages generated during cyber attacks, if the memory elements affect if the memory elements affected by soft errors are those containing the autoencoder weights, we verify that what may happen is that up to the 79% of legal transactions may be erroneously recognized as illegal, thus making such transactions inhibited. And so the system will actually result unavailable to the user that needs to perform such a transaction. So this in this specific case, the limited reliability of hardware accelerators implementing autoencoders used for security purposes could actually put a risk and make the whole system result unavailable for the user. And so we will have impact on system availability and of course, impact also on security. And similarly, on a similar issue, if for instance, we consider aging phenomena that might affect hardware blocks, and typically these are ring oscillators that are used to secure data again, accordingly to physically unclonable functions, we verify, and also this research has been presented within a paper that is currently under review, that what may happen due to aging is that the oscillation frequency of ring oscillators may change. And so the key generated for the user authentication may change over time, and consequently the authentication of legal users may fail. So the system will result unavailable to users that actually need to access those data. And so again, the limited reliability of the hardware blocks that are used for security purposes will make the system unavailable, and so put at risk the availability of our system. And of course, we have an impact also on security. So all of this shows how much the reliability of the component blocks of our autonomous machine is relevant in order to meet not only the global reliability target at the system level, but also the safety, security, and availability goals that we have for these machines at system level. And for those who are interested in the technological challenges for reliable, safe, secure intelligent systems, we created within the IEEE Computer Society a community in the form of a special technical community on this topic. We also have a project within the IEEE Digital Reality on this topic, and so all of you are more than welcome to join us if you have interest in this field. We are also performing some activities, and particularly we are completing policy documents, one on AI and one on autonomous connected vehicles within the IEEE European Public Policy Committee working group on ICT that I'm chairing. And again, if you are interested in this topic, please contribute to our activity within the IEEE European Public Policy Committee by replying to the call of engagement that you can see reported here. So to summarize, I believe that reliability is a global constraint for highly autonomous machines. It should be satisfied not only in itself at the global machine level to meet our autonomous machine, to make our autonomous machine operate as planned, but also at the machine hardware component level in order to meet the machine's reliability, availability, and security and safety requirements. Numerous are the technological challenges to be faced, but several are the solutions that are currently investigated. So I hope that reliable, safe, available, and secure highly autonomous intelligent machines will soon become a reality, and I hope this will happen for the benefit of humanity. This concludes my presentation. Thank you.
Thank you so much, Professor Metra, for the insightful talk. We'll save all the discussion and question at the end of the all the talks. We will have a discussion session. So next we have Professor Yuhao Zhu to present more specifically on the software reliability in autonomous machines. So welcome, Yuhao.
Okay, yeah, thanks, Shaoshan, for the invitation, and thank you, Professor Metra, for the very insightful talk. So I'll talk a little bit about the software side of autonomous machine and improving and harnessing software resiliency in autonomous machines. So to begin with, I like to just make a point, which is perhaps very obvious to all of us, that autonomous machine software stack is very complicated. And what we are showing here is a grossly simplified software pipeline of a typical autonomous machine. It includes many different components, like localization, object detection, tracking, planning, and control, and things like that. Some of these components are actually sort of being eaten away by neural networks or be implemented in neural networks, such as things that in the perception module, but there are still a lot of other modules, such as prediction and planning and control, that are implemented in non-neural net algorithms. Because of the increasing complexity of the software stack, the autonomous machine software stack faces a range of traditional and emerging reliability issues. And some of them, like soft errors, are more classic and traditional, but things like adversary attacks that are specific to neural nets are more sort of emerging new forms of reliability issues. So the game plan of my talk today is going to be sort of twofold. I'll first talk about how we can defend against adversary attacks on neural networks, which, as I said, is widely used in the AM software stack. And then I'll expand the scope to the entire software stack to consider things that are not based necessarily on neural nets, and how do we sort of protect the entire software stack. And that's the game plan today. So let's start with adversary attacks. So as some of you might know, adversary attacks are essentially perturbations, small perturbations applied to the input images, and those perturbations would essentially mislead a neural net to mispredict. For instance, a stop sign could be predicted as a yield sign or speed limit sign. There are primarily two countermeasures of adversary attacks. One is adversary training, in the sense that you mix, at the very high level, you mix the adversary samples into a training set so that the network is trained with the knowledge of the adversary attacks, with the hope that it's going to be more robust against attacks at the inference time. The problem with adversary training is that it necessarily makes a trade-off between robust accuracy and standard accuracy. So standard accuracy is accuracy when the network is inferenced on clean inputs, and robust accuracy is the accuracy when the network is inferenced on adversary attacks. So it necessarily makes a trade-off. The second countermeasure is adversary detection, in the sense that we have some sort of mechanism to detect whether a particular input is an attack or not. And if it's an attack, we can sort of throw away or maybe re-execute. There are a fail-safe mechanism that can be employed once an adversary is detected. The problem with adversary detection is that there is typically a high detection overhead. And so in our experiments using state-of-the-art detection algorithms, the overhead is typically 1 order of magnitude higher compared to the inference itself. And a side effect of detection is that it doesn't really generate the correct results, right? It tells us that this is an attack, but it doesn't know what to do with it. So our goals are to simultaneously ensure high robust accuracy and standard accuracy, do that in a low overhead way, and eventually we ideally want to emit the correct prediction upon adversary attacks. And our key idea is what we call adversary aware network specialization. I'll talk more about that in detail, but the high level bits are, we have a lightweight mechanism to detect the adversary at runtime. And then depending on the characteristics of an adversary, we can dynamically condition or reconfigure the rest of the network to adapt to the particular input. That's the high level idea. So this is the sort of high level illustration of the end-to-end network or pipeline. There are two components. The first component is what we call the prefix layer, which is essentially a set of, you can think of it as a classifier. It doesn't have to be neural nets, but it could be implemented as just a few convolution layers. And the job of the prefix layers is to classify inputs, essentially detect the strength of a particular, the attack strength of a particular input. If it's a clean input, well, then the strength will be 0, and which we denote using lambda. And so that's what the prefix does. It generates the adversary attack strength, or it predicts the strength. And given the strength lambda is going to be the input to the suffix layers, and the suffix layers are so designed that it can reconfigure itself depending on lambda. So at the high level, you can think of it as dynamically reconfiguring the rest of the network depending on the characteristics of the input. If lambda is 0, meaning it's predicted as a standard input, well, the network is going to fall back to, at the high level, fall back to the standard network. If the attack strength is high, well, then the network is going to be reconfigured to essentially be specialized to predict the correct output, even if the input is a strong attack. That's sort of the high level idea here. So there are two questions. One, how do we detect the attack strength of a particular input? And two, how do we dynamically reconfigure the rest of the network? So to detect a particular input or to classify a particular input, our idea is based on the observation that a benign input in an adversary attack typically exercise different paths of a neural net. So, and when I say path, I'm talking about the collection of important neurons. The magnitude of the neurons are, highly activated neurons with high magnitudes, and the connections between these neurons. And that's the connection of important neurons, and then connections between them is what I loosely define as the path. And so, you can think of the activation path as sort of a program path. It's input specific, and so what we found is that activation paths for benign inputs are very similar to each other, to the particular path corresponding to the class. The activation path of adversary inputs are typically very different from the path that corresponds to the class that's predicted. And so because of this difference, we can train a regression model to predict whether a particular input is an attack or not, or even better, the strength of the attack. And that's primarily based on this observation that the path similarities are similar for benign inputs and very different for attacks. And so with that, we can generate the attack strength lambda, and this lambda goes into the suffix layers. And the suffix layers primarily provide two knobs for us to reconfigure itself. The first knob is to select a range of different kernels. Each kernel is specialized for a particular attack strength lambda. The other knob is the batch normalization layer, or the choice of different batch normalization layers, which is shown to be sensitive to attacks. And so essentially, using lambda, we can choose between or switch between a set of different convolution kernels and a set of different batch normalization layers, and a unique combination of these two essentially constitutes the suffix layer, which is specialized to a particular attack strength. So I won't go into the details of the results, but I'll show you some headline results. So the prefix layer, in this particular implementation, there's certainly a range of different implementations you can imagine, but in this particular implementation, the prefix layer is ResNet 18 and the suffix layer is ResNet 34, and we evaluated this in this particular case on CFA100. And the baseline is a very commonly used PGD adversary training setup. And you can see that depending on how you perform the adversary training, there's always a trade-off between the standard accuracy on the x-axis and the robust accuracy on the y-axis. And our system is able to sort of combine the best of both worlds and achieving simultaneously high robust accuracy and standard accuracy, because we're able to dynamically decide the characteristics of a particular input and specialize the rest of the network for that. Okay, so that's just the neural net. Now, if you look at the entire software stack, and so admittedly, this is a bit of an eye test. The point is not to kind of look at every single node here. This is the ROS graph of AutoAware. And as you can see, just one tiny little node or just a few collection of nodes in this ROS graph are implemented using neural nets, and the rest of them are essentially non-neural net algorithms. So protecting neural nets as much as is important is not enough. We need to expand the scope and look at the entire software stack. Now, the key idea or the observation here is that the autonomous vehicle software has inherent error masking attenuation mechanisms. So I'll talk about what these mechanisms are and some, at least samples of them. And then if we can intelligently leverage these internal inherent mechanisms, then we can reduce the protection overhead. For instance, we don't necessarily have to perform temporary execution if the error is inherently masked by the software, right? That's sort of the high-level idea here. So, so these are empirical studies, and so I'll just go over a few different mechanisms that existing software stack employs to mask and attenuate errors. So there are two examples of error attenuation. One is a low pass filter. So typically these algorithms like common filter would employ things like low pass filter. So if you have a high frequency signal through a low pass filter, the high frequency signal would essentially be attenuated, and you can think of it as attenuating the errors. It doesn't necessarily mask the errors, but it would reduce the strength of it, and that to some extent would mitigate the error. And so here error, it could be either a bug in the software, it could be an adversary attack, it could be even soft error from the hardware, right? So low pass filter is one mechanism for error attenuation. Another mechanism is a lot of times in autonomous machine software, you have to apply numerical algorithms for integration, for instance. In numerical algorithms, it's iterative, and so every single step, the impact of every single step isn't as much, right? And so if you have one erroneous signal in one particular step, the integration result in the end is probably not going to be affected as much. So iterative integration is another example of attenuating the errors. It's an inherent mechanism baked in the algorithm. There are other mechanisms to basically mask errors. For instance, virtually all autonomous machine software perform multi-sensor fusion. So to detect an object, for instance, typically people fuse the object detection results from point clouds and from the cameras. And the fusion operation typically, let's say, is a union. So if one of the paths, let's say the LiDAR point cloud object detection, the result is completely wrong because of the fusion operation, as the end object prediction, object detection result is still intact. And this multi-sensor fusion is one inherent mechanism that basically masks errors. Another case is where the masking is conditional. So state machine is very commonly used in the software stack. And if you're not in a particular, if error happens in one particular state, but the state transition doesn't really go through that particular state, well, then the error is inherently masked as well, right? And so this is the conditional masking. And so based on the analysis of these inherent masking and attenuation mechanisms, we provide a set of APIs for error masking and attenuation. Essentially, developers would write or develop their software stack using our APIs, and each API is either for a particular masking mechanism or a particular attenuation mechanism. And at runtime, when these APIs are executed or triggered, well, the underlying system can naturally relax the protection because the underlying system knows that some error masking is going to take place or attenuation is going to take place. So we can relax the protection, for instance, avoid the temporal re-execution. Right, so I won't go into the actual implementation details, but I'll again show you some headline results. So in this figure on the x-axis, we sort of emulate or inject faults into some of the nodes in the ROS graph of AutoWare. And the y-axis is the error propagation rate, which is the probability that a particular error in that node is propagated to the vehicle, like it leads to a crash. And we're comparing against 4 different mechanisms. One is the orange bar is no protection, meaning it's just running as is and it doesn't provide any protection. Well, we just don't do any software hardware protection to the software stack. And the second mechanism is the green bar here, which essentially performs an outlier detection and remove outliers at the inputs to each node. And the yellow bar is essentially re-execution. We always we first detect the outlier for every single output, and then if the output is an outlier, then we re-execute, and this would conceivably protect against soft errors because of re-execution. And this blue bar is our mechanism, and as you can see, our mechanism has significantly lower error propagation rate. And at the same time, the average runtime is also much lower compared to the other protection mechanisms. Obviously, the runtime it does add runtime overhead compared to the no protection case, because we do perform things like re-execution, but we do that selectively based on the characteristics of each individual node. And we know that because we provide a set of APIs that developers use, right? That's the high-level bits. And so to conclude, I think autonomous machine software is getting increasingly complex, facing a multitude of reliability issues. Some of them are classic, like soft errors, and some of them are emerging new forms of issues like adversary attacks. We have to protect against both. And I think one thing that's incredibly interesting going forward is to leverage the software inherent masking and attenuation mechanisms to intelligently reduce the protection overhead. So with this, I'll conclude. And so the work is primarily led by my student Yimin Gang, who is the first picture here, and also with the help of all other students. With this, I'd like to thank you.
Well, thank you so much, Yuhao. It's very interesting work with very encouraging results. As we deal with ever more complex software systems in autonomous machines, software reliability is indeed becoming more challenging. So thank you for your work. So next we will hear perspective from the system side, presented by Zishen Wang. He will discuss system reliability in autonomous machines. Zishen, the stage is yours. Zishen, are you muted?
Yeah. Sure. Yeah. Thanks, Shaoshan, for this kind instruction, and thanks Professor Metra and Professor Zhu for these very insightful presentations. And hello, everyone. I'm Zishen, and I'm very honored to be here to have this chance to share some of my thoughts on this reliability of these autonomous machines. So I will discuss of this mainly from the system perspective. And before diving into these reliabilities of these autonomous machines, I want to take a minute to introduce how I view this system. So first, we know these autonomous machines is a very broad concept, and it includes from the small scale, this a drone spawn robot to this large scale self-driving cars. So all of these autonomous machines are inherently very very costly. So spanning from the algorithm to the system and all the way down to the architecture and hardware. So for the algorithm layer, you can see we have the many different algorithms and kernels in the perception, localization, planning, and control stages. And all, we also have this learning-based schemes, so with supervised learning or the reinforcement learning. And for the system layer, as Professor Zhu just mentioned, we have this robot operating system, the ROS, and it's usually built on top of some the runtime to dynamically distribute the workload to the proper compute substrate. And for this hardware layer, we have these different types of the compute platforms and different types of the sensors. So basically from the reliability perspective, so each level of the computing stack is potentially vulnerable to the errors. So the errors can propagate horizontally with their layer, or also can propagate vertically through this cross layer. So so what sources of the errors exist in this autonomous machine system? So here I just name a few here and divide them broadly into four classes. So the first is errors in the hardware, including the faults in the memory and faults in the compute, such as a bit flip, or what is timing errors. And second class is the errors in the software or the runtime framework, either propagate from the hardware or due to some overly aggressive implementations, such as the low precision or the software approximation, etc. And the third class here is the attack on the model, the target hardware errors, the row hammer attack, or some adversary attacks on the model, like the Professor Zhu just mentioned. And the fourth class is the errors or the variations from the sensor data, such as the variation in the input images or some adversary or the data processing attack on the inputs. So all of these different type of errors will impact the safety and reliabilities of the autonomous machines. So next, what I will do is I will pick few types of the errors and discuss how they impact the safety of the reliability of these autonomous machines. And I will use the drones and cars as two examples because they represent the small scale machines and large scale machines to show this impact. So the first I will discuss the sensor variations in the drone system. So here we explore the impact of the depth image noise on this RGBD camera systems on this drone performance. So you can see here this drone navigate in this environment, and we inject some noise like this Gaussian noise in the depth reading of the camera. So you can see this noise will disrupt the sensor images or these representations of the environment. And what we find is after we inject this Gaussian noise in this camera, it will inflate the obstacles and make this obstacles obscure. So that makes the drones to replan its trajectory more often. So the number of the more replans, it will consume more flight energy and more flight time with like from the start location to the end locations. Like will degrade the system performance. And also we can know that when the noise is beyond a threshold, it can even like make the task fail. So you can see like there's 10% of the task fail with like higher noise. Yeah. So and like for like sensor variation in these autonomous cars, so we know like the different weather conditions will bring the different brightness and contrast in the image capture images, and will like have different impact on this car's performance. So for example, here like with the 3 different brightness and contrast level of the camera on this like Baidu like Apollo platform, we can see the accuracy will drop with the like more severe brightness and more severe contrast in this like computation study. And also we can like notice that so with some like sensor like a fusion spin in this like a green car against like a green bar, so the accuracy will improve. So that so we can see like this the brightness and like contrast will degrade the system performance, but with some like sensor fusion, it will like help some resilience. And going beyond this like camera, we also have this like LiDAR on these autonomous machines. So for the like LiDAR, we consider two there's 2 like noise model here. One is the drop filter, which means like the part of the like point cloud is lost during this process. So you can see with the higher percentage of the drop loss, the accuracy of this like obstacle detection, the lane detection will drop. And also you can see like compared with this camera and LiDAR, you can see this the LiDAR noise has more impact than the camera noise in this study, because this study is like conducted on the Baidu Apollo, and this like platform is heavily rely on this like LiDAR processing. Yeah, so this is like the impact of the sensor noise on these autonomous machines. And next, I would like to pick some like hardware noise as an example to discuss is the impact on these autonomous drones and autonomous cars. So you can see like this is like the flow of this this is a drone flow. So the data will come from the environment and go into the sensors and through the compute, and like send this like result to the actuators to like send this like a flight command. So I think like Professor like Metra have discussed the like a hardware fault in the sensor will have like a huge impact or pose threat on the safety of these autonomous machines. So here I want to shift a little bit to discuss if the hardware fault, like the bit flip, transit fault, permanent fault, like occurred in this compute stage, how this fault will impact this whole system. So actually, like you may know that there's like a lot of study in the like fault injection in the CPU and like GPUs like priorly. So the most of the like prior works, they like focus on like a single kernel, what is isolated kernel. For example, they inject noise or is inject like a bit flip in the input of the algorithm, and directly observe the direct output of the kernel, and to like say like the how many percentage of the silent decryption, how many percentage of the deny, crash, and hang. So like in this autonomous drones or these autonomous cars, it is like a cyber physical system where it's end-to-end system. So what I mean the end-to-end system here is after the like error happening in one stage, it may propagate to the whole stages and finally impact the like drones like action with cars action. So during this like process, the error may like mask or also may like exaggerate. So we have to like look at this whole system from end-to-end like perspective. So you can see like, for example, this the like 2 trajectory on the right. So inject this the fault in the perception stage. So like when there's no fault, you can see the drone like can navigate from the start location and navigate to the end location without collecting into these obstacles. But after we inject some fault, this fault like may propagate through the stages and finally make the drone to have the wrong action. So it may like have this wrong find command and collect into the obstacles. So that means like we have to calculate or like characterize the system like resilience from its end-to-end perspective. And also like want to like mention that we also need some like appropriate fault injection framework. For example, many robotic workloads are based on this ROS. So we need like a ROS injection framework that can adaptable with the ROS. So here, like, for example, we can make this fault injection as a ROS node and interact with the like different like ROS like node or is ROS like a topic of the like other parts. So for example, we can inject the fault in this motion planning and let this fault like propagate to the control stage and interface with the air sim with this like drone simulator and to finally like impact this like quality of flight. Yeah, so like basically it is the suitable fault injection framework is very important with like kind of analysis. And yeah, and here like I just like highlight some result. So like if like you can see like if we like look at this the single kernel in the isolation, we get this reliability of the each kernel. But if we let this error like propagate through this whole perception planning control system, and to evaluate its final impact, we can see the final impact may be like a different from the isolated kernel evaluations. So that like just like motivate again that we need some like system like level characterizations of these reliability issues. So going beyond from this like drones to cars, so we can see like cars, is a more like a complex system, but also the fault can have like very huge impact on these cars. So you can see like we inject fault. So like this work like inject fault in this compute stage of the like its perception planning or its like lane prediction of the cars, and it will like finally can like cause some like this car like clogged into the like can cause some like collision. And also like one thing here I want to mention that is we need to define some the appropriate metric or this resilient centric metric to better evaluate this system reliability. For example, like we can like incorporate our domain like knowledge using some like stop distance or safe distance to evaluate is the whole like car system instead of only the accuracy or like performance. And also I want to highlight here that because the car is a very like a complex system. So if we randomly inject fault in the like in a whole like a system, it is very high likely that the faults will not like violate these like safety violations, right? So that means like we need like a very large amount of time under test. So we need some like a sort of intelligent way to find these critical locations. For example, we can leverage some of the learning-based or like a patient-based fault injection. So can find these situations and faults that are most likely to lead to this violations of the safety conditions. And also like I want to briefly mention this fault detection and mitigation, because the final goal is to want to enable the safe and reliable autonomous system. So fault injection is to know like which part is critical and to know this resilience of the whole system. But we also need to to detect the fault and mitigate this fault impact after fault happens. So here I want to make 2 points here. So the first is like in this drone system, what is edge autonomous system, because it's very like size, weight, and power constraint. If we directly replicate the hardware or use this hardware redundancy, it works, but it may it incurs very large overhead. So this redundancy scheme may not very suitable for these edge applications. So that means we need to propose some lightweight fault detection and mitigation scheme here. For example, here we use this anomaly detection to monitor some critical variables in this perception planning control pipeline. So if this a value is distorted from its normal values, we know there maybe some error happen here. So use this very simple 2-layer autoencoder for this anomaly detection. We can very easily detect this the whole system without costing too much. And also as we mentioned before, is the robotics are often based on the robot operating system. So we can also make this fault detection as a ROS node. So this part, so this detection scheme can portable to any kind of this ROS-based system. And also for the cars, so for the cars we also want some lightweight and effective fault mitigation and detection. So here for example, this work they leverage some of the input data temporal diversity in the input data. For example, in like two consecutive images, because the car like move a little, the pixels of each image, it will like differ a lot. But we can see that the images are very like similar because they are like in the adjacent frame. So that means the compute will like generate the same output or very similar result based on these two images with like two different pixels. So that means like we can send these two consecutive images into two agents and let them like compute like separately and compare their result. So basically they should like generate this very like similar output. So in that way, we use some like a software level, this like an input data diversity to like detect this like a hardware fault. So this very like a lightweight compared to this like a double like module redundancy or triple module redundancy, but it's like very effective. And also it can like plug and play solutions for this type of applications. So to like summarize, I think this autonomous machine system, across their like a system where errors can either in the sensors, software, hardware. So all of these like errors can impact this safety. And this fault analysis for these machines need to be end-to-end assessment that can accurately model these error propagations. And also for the fault detection and mitigation techniques, they need to be like lightweight and they need to be this like a plug and play, this very like portable. And also we need some like accurate fault model or this better like a metric to better like characterize the fault impact. And we need some intelligent way to find the safety critical faults. And like in the design, we also need to consider the resilience as the first one of the first order the first order of like objectives in this autonomous like system design. Because for now, I feel like the many design they more focus on the high performance, the more energy efficient. And after the design framework, they will they will evaluate its like resilience. But if we can like take the resilience as one of the design factor in this design to like maybe a better, and also we can explore this compatibility of the errors in this system, especially the system with so many like moving parts. Yeah, so this is like my part. I would like to thank my collaborators, and yeah, I will like hand over to Shaoshan. Thank you.
Thank you very much, Zishen, for another great talk with very insightful research results. At the system level, when we deal with reliability, we are dealing with many different pieces of software and hardware components. It's indeed chaos management with elegance. So next we will hear from the industry perspective from Dr. Bo Yu, who has worked in the industry, particularly in autonomous driving in the past 6 to 7 years. So Dr. Yu, the stage is yours. Dr. Yu, are you muted?
Yeah, sorry about that. Thanks, Shaoshan, for the invitation and introduction. So today's talk is about latency-aware computing system design for autonomous vehicles. Yeah, I will first talk about the design challenges of computing system for autonomous vehicles. I will show that the latency variation of computing system is quite large, and this large latency variation is harmful to the safety of autonomous vehicles. Then I will take the localization software as an example to show the design method we propose to mitigate the latency variation. And at last, I will briefly talk about a digital twin-based simulation for autonomous driving, which could help to evaluate and verify the performance and safety of autonomous driving system in a very efficient way. Autonomous vehicles have become more and more popular these days. So in China, robotaxi fleets have begun to run on the road, and in China also, almost every newly made electrical cars is equipped with level 2 autonomous driving system. We know that the high performance computing system is the brain of these vehicles. So design a high performance and reliable computing system is critical to autonomous vehicles, and is quite challenging as well. So the power consumption, latency, and the functional safety are the most important design goals for autonomous driving computing system. In practice, functional safety is achieved by using highly reliable chips and using redundant computing components, and by applying safety-oriented development process. This talk is not about functional safety. We will focus on latency. So latency and power consumption also affects safety and reliability. So for example, high power consumption leads to high heat dissipation, which may cause the computing system in a unstable stage or causes the vehicle even to crash. Long computing latency will lead to long braking distance. It may also cause the vehicle lose control when the vehicle is at a very high speed. But optimizing the power consumption of the computing system is quite challenging because the autonomous driving software is quite complex and computationally expensive. And optimizing the latency of the computing system is a challenge as well, as the processing pipeline is quite long. A typical processing pipeline that after the sensor data is captured by the system, the perception module will fuse the sensor data to calculate the ego pose of the vehicle, and also will calculate the states of other vehicles and pedestrians. With the results of the perception module, the decision module will plan a safe and comfort path. And the controller will drive the vehicle, will control the vehicle along the path. Having the power, latency, and performance design goals in mind, we designed a computing system of which software pipeline is shown in the figure. And the table lists the algorithm we used for perception, for localization, and for planning. Based on our evaluation of power and latency on FPGA, CPU, and GPU, and also considering task level parallelism, we proposed a optimized computing system using FPGA, NVIDIA GPU, and Intel CPU. In our system, FPGA is used for sensor interface logic and sensor pre-processing. And the GPU is used for running perception task, and the CPU is used for localization, planning, and control. So here is the evaluation results of our own autonomous vehicles. The power consumption is about 120 watts, and the average end-to-end latency is about 160 milliseconds. So one of the key findings is that the end-to-end latency shows a large variation. The longest latency is about 300 milliseconds. It's nearly 2 times of the average latency. So the design goal of the computing system for autonomous driving is not only to minimize the latency, but also to reduce the latency variation. So we use localization as an example to show the cause of latency variation and show our proposed method to optimize latency and latency variation. So in general, autonomous vehicles use SLAM algorithm to build a map and localize itself in the map. Here is a typical SLAM algorithm. It consists of 2 parts, the front end and the back end. The front end associates sensor measurements with physical landmarks from consecutive frames, and calculates initial estimate of the map and the ego vehicle's pose. The backend typically use an optimization method to further refine the accuracy of the map and the ego pose. We implement the SLAM algorithm on our computer system of our vehicle. So by profiling the algorithm, we have several findings. The first one is that compared to the front end, the back end shows higher variation. The second one is that the latency of the back end correlated to the number of tracked features in the front end from the environment. So it means that the latency variation of the back end is caused by the dynamic environment. Based on these findings, we propose two kinds of strategies for localization accelerated design. For the front end, since the latency variation is small, so the design goal is to minimize the latency and to improve frame rate, frame throughput under the area and the power constraints. So here is front end accelerator hardware architecture. The pipeline and on-chip memory microarchitecture are carefully optimized and designed, which guarantee the front-end hardware can receive the high frame rate sensors. The high frame rates of images enables high performance feature checking and will give better results, front-end results. So for the back-end accelerated design, the design goal is to reduce the worst case latency. A straightforward method is to design accelerator that take accounts for the worst case. But we found this approach will waste computing resource at runtime. We would like to design a runtime adaptive backend accelerator. So there are two challenges to design this kind of a runtime accelerator. The first one is that at the backend, use optimization algorithm, and this algorithm is quite complicated, and the operation is irregular. So manually exploring the design space to get an optimal solution is quite difficult. So we need a design framework to help with the design space exploration. The second challenge is how to adapt to the dynamic environment at runtime. Since autonomous vehicles typically operates in dynamic environment, like indoor environment and outdoor environment, so which will affect the workload at runtime and lead to latency variation. But a static accelerator design only considers worst case and will result in wasteful computation. So the challenge is that if we can utilize workload variation, utilize latency variation to optimize computing resources at runtime. So here is our solution to overcome the challenges. We propose a design framework. The framework uses the macro data flow graph to model the algorithm and to simplify the design space exploration. And based on the data flow graph and the domain knowledge, we designed a hardware template. The template has several customizable blocks whose power and latency can be tuned through a number of parameters. So given the design constraints and the parameters in the hardware template, a constraint optimization problem is formulated. And a optimal design point can be obtained by solving the optimization equation, and then we get a optimized static design. And at runtime, the framework can close some hardware blocks through clock gating to reduce power according to the workload variation, while not affecting the accuracy and the latency of the hardware. Here shows some design details. The figure is hardware template, which is constructed from data flow graph. And the formula on the left shows the optimization problem we formulated. And given the design constraints and the static optimizer will determine a optimal static design under the design constraints. And the red figure explains why the runtime optimization can work. We find that the iteration number of a optimization algorithm is correlated to the number of checked features. So for the worst case, it needs to iterate the maximum times, but for the other cases, the number of iteration can be reduced. So the customizable blocks can close some computing units to save power while not affecting the performance. Here is the evaluation results. The left figure demonstrates the effectiveness of the static optimizer. The results show that the automatic synthesizer design are at optimal designs, and red figure showed that compared with Intel and ARM processor, power and the performance of the static design are greatly improved. And we also find that the runtime mechanism can save extra 10 to 20 power consumption compared with the static design. The last part is about simulation tool for testing and evaluating autonomous driving software and hardware. In practice, testing autonomous driving software and hardware is quite expensive. Keep a number of autonomous vehicle running on the road is expensive. Also, evaluating the latency, power, and safety of the computing system needs a large amount of data. So collecting these data from various environments is expensive as well. So we propose to use a digital twin-based simulator to reduce the testing and evaluation cost. The digital twin simulator shown in the left figure includes a digital twin map and high fidelity sensors and vehicle model. With these components, the digital twin simulator can generate sensor streams in various scenarios to the autonomous driving software and receive the control commands from the software. So it supports end-to-end software in-loop test and also supports hardware in-loop tests. So we find that by putting the physical tests into the virtual environment, the testing and the data collection costs can be greatly reduced. So to recap the talk shows that large latency variation exists in computing system for autonomous vehicles, which is harmful to the safety of autonomous vehicle. And our approach to design a latency aware localization accelerator is presented. And at last, a digital twin-based simulator for verifying and evaluating performance and safety is briefly discussed. And a lot of work presented in this talk is collaborated with Professor Zhu and Dr. Shaoshan Liu. Thank you very much. That's the end.
Well, thank you very much, Dr. Yu, especially for presenting us with some very interesting industry insights. Especially, I noticed that the simulation tool used in the industry. It would be great to see more reliability metrics being integrated into the tool. So now we have finished with all the talks. Now we entered into the discussion session. We will spend about 15-20 minutes to discuss and debate. Hopefully it's a fruitful session. So we have prepared some interesting questions, one for each speaker, but hopefully the speaker, if each of you have some questions towards each other, that would be great as well. So I would start with Professor Metra. So the question is as follows. Through the past few computing technology eras, including personal computing, mobile computing, and cloud computing, reliability has been a consistent theme. What are the lessons learned through those eras, and how is autonomous machine computing different, and what are the unique challenges that you see?
Thank you, Dr. Liu, for the interesting question. And of course, congratulations and thanks to the other speakers for their very interesting presentations. So I think that a lesson learned that we could say is that basically, I would say reliability is always there. So it has been, let's say, a recurrent theme for all the technology that took place in these years into the evolution. And basically this because I think we would like our machines to operate as we would like them. So it has always been there, at least as a goal, as a final objective or a desire. Again, because we would like our machines to operate as we design them to. But the issue is that the technological challenges, as we heard also in this presentation, that we have to face in order to make our machines reliable really change continuously with technology, because of course, even thinking about the microelectronic technology, the faults that I'm talking about, the faults in the hardware especially, they change with technology. And so this is, let's say, a recurring or continuous goal and objective for the various technological evolution. And of course, it's always presenting new challenges because basically the faults will change. And the peculiar aspects of autonomous machine computing, I think that it's very computing intensive, as we know. And that in addition, if you think about fully or high-level autonomy system, the human surveillance is no longer there. And so really reliability, in addition to be something that is desirable and was desirable also in the past, even for general purpose applications, I would say, then becomes a need, as we heard also today in the various presentations of this panel. So it's a need as well as safety, functional safety, especially, and security. So they become really of primary importance. And one big challenge I may think about the future is the ability to create machines that not only have a huge memory and huge computing ability, but also have some sort of, let's call it consciousness and hurt. Or maybe this will remain prerogatives of human beings, but at least to make them able to take actions based also on some ethical principles, so to be able to make them learn how to face unexpected in, let's say, possibly ethical way also. That will be a wish for the future and a challenge, I guess.
Well, thank you very much. And a follow-up question regarding that, especially regarding your another responsibility, which is the public policy side. What do you see can be done in the public policy side regarding standardization on reliability? Because traditionally reliability, although it's a very important issue, it's not as important as they are in autonomous machines. As you said, autonomous machines are without human supervision. So what do you like to see on the public policy side?
So not that I'm an expert in that, but we do some activity within the IEEE European Public Policy Committee. And so I believe that really we need, the hope would be internationally recognized and shared standards in the field, and also legislative framework in the field that could of course, these are complex issues because they involve also legal aspects, ethical aspects, and not only technological aspects. Of course, as far as we know in Europe, they're working a lot on these. So even within the IEEE, there are some standards that have been developed and proposed related to functional safety and various aspects. But even within the IEEE Computer Society, but of course to have a common internationally recognized legal framework for autonomous systems would be desirable, and I would say would be needed, really needed. And so there is a lot of work that is being done in this field. Let's hope that soon we will have we have a solution to this, let's say, responsibility, liability, and ethical responsibility concern. Because without them, yes, it will be very difficult. Even if from the technological point of view, we are all technologists, so we are working a lot to solve any challenge. At the end, we would need also really standards, as you mentioned, and a common, I would say, legislative framework in the field.
Thank you so much, Professor Metra. Now it's a perfect time to transition from the public policy side to industry side. So Dr. Yu, you gave a lot of practical insights regarding autonomous machine reliability. So what are the reliability pain points that you have observed from industry perspective?
From my point of view, there still lacks a safety architecture for the computing system for autonomous vehicles. For example, at the hardware layer, it's still challenging to design a high performance and functional safety, say ACOD level SoC. At the operating system and middleware level is a real-time and functional safety operational system and middleware system are still highly required. At the algorithm level, I think there is no good solution for design a autonomous driving software that meets the intended function safety, which need to consider the environment. And at the tools level, I think we need a more powerful simulator that can integrate more physical elements into the simulator and further reduce the testing and validation cost and move more test and performance verification tasks onto a virtual environment. Yes, that's my answer.
Thank you, Dr. Yu. So as Dr. Yu mentioned, there should be cross-layer collaboration to take care of reliability issues. So Professor Zhu, since you focus on reliability from the algorithm and software side, what are on your wish list of hardware or architectural supports for your work? Do you think software reliability techniques are more flexible compared to the hardware ones?
Yeah, well, I mean, I think it's certainly the case that software is more flexible than hardware. And I think one thing that's perhaps a little overlooked in the past in terms of protecting software is to, well, basically analyze the inherent mechanisms baked in the software that can attenuate and even mask errors. And I talked a bit about that in my talk as well. And that's, I think, especially true for autonomous machine software developers. I mean, because it's high stake and developers tend to building lots of error tolerant mechanisms into their algorithms, things like, as I said, low pass filter, and sometimes when you do numerical integrations, I mean, the software is to some extent, the algorithms are developed to some extent to protect itself. And so in that sense, I think it would be very interesting to leverage these inherent mechanisms in the software to lower the hardware protection overhead. But I think the hardware needs to provide the necessary knobs for the hardware, for the software to do so. For instance, ARM cores, for instance, provide things like dual core lockstep execution, which essentially allows you to do to employ dual module redundancy. Well, that's the hardware mechanism that needs to be provided for the software to take advantage of that, but it needs to be more flexible. For instance, it would be nice to, at runtime, dynamically configure the cores so that it can switch between this lockstep execution versus the conventional multi-core execution. And this dynamic reconfigurability, as far as I could tell, is not there in today's hardware design. It typically is configured at the boot time. And so it would be very nice to investigate into the hardware support that provides this dynamic, fine-grained, and very lightweight reconfigurability, so that the software can take advantage of this and decide, well, if this piece of software is quite safe because the algorithms are developed with safety in mind, well, then we don't necessarily have to pay the much harder overhead to protect it. And for this piece of code in this particular time, well, there really isn't any masking attenuation mechanism, well, then, you know, the hardware needs to come in and provide strong protections. And so that's one side of the story. And then the other is, how can software developers help? I think that it's hard to, it's certainly possible, but it's hard to formally provide specifications for safety for a piece of complicated software as complicated as autonomous machine. I think developers have insights, right? When they write a piece of code, they know, well, this piece of code that I wrote has these masking attenuation mechanisms, and we need to empower developers to express these intents to the online runtime system. And I think what's going forward will be important is to provide dedicated safety-aware or reliability-aware APIs that allow developers to express intent or the strength of protection in their algorithms. It's a bit like the pragma in OpenMP. You know, when a particular programmer writes a particular piece of for loop, the program can express the fact that this piece of for loop is perfectly parallelizable, so go ahead and parallelize it. Similarly, we can imagine similar pragmas where programmers could say, well, this piece of code, this API call is probably going to be very safe because I'm already doing outlier detection. I'm already doing low pass filtering. So, you know, if your protection budget is limited, or don't spend the protection budget on me, spend it somewhere else, right? And I think, you know, the point is that the software has inherent mechanisms, and we need to empower the developers to express those mechanisms explicitly, so that the hardware can be, you know, the hardware protection overhead can be lower. That's sort of my thoughts on this.
Thank you so much, Professor Zhu. So let's now look at, let's flip the coin and have a question for Zishen. Since you focus on reliability from the hardware and system side, what are your wish list of tools that can help your research? How do you see software reliability techniques and hardware reliability techniques can interact with each other?
Sure. Yeah, I think this is like a very great question, Shaoshan. It's exactly like what we wish, or the difficulty we faced when we do this research. So I feel like the missing part, or the part that we want to is a co-simulation framework between the architecture, what is hardware simulation, and this drone, what is called is autonomous vehicle simulation, right? For example, if I want to evaluate this hardware fault on these autonomous machine applications, the one way we can do is we directly inject fault in this software stack. For example, it's a color with an LSIM, or it's a drone simulation. So it works it's pretty fast, but the thing is we're not sure whether the fault we inject in this software software with a high level framework is accurate enough to model the real hardware fault, right? Yeah. So and also we're not sure whether it can achieve very great fault coverage of this kind of low level fault. But if we inject this hardware fault in this low level simulator, like this RTL level, it's very accurate, it's correct, but it's pretty slow, especially in many cases, there's no good interface between this low level simulation and high level simulation. So sometimes it's even impossible. So I think if we can have some co-simulation framework between this hardware level simulation that running on this full stack, and it's a high level this application simulator, and if we can have this framework, so I think it will open a door for many kind of this resilience, reliability with robotics evaluations experiment. Yeah, and in terms of your a second question, from this hardware and software level, yeah, I do believe they can interact with each other, and there's a lot of opportunity here. So one thing is you can say many fault, for example, is bit flip, or is memory fault, or is compute fault from the hardware side. When they propagate through this whole system, they may mask or even exaggerate in some places. I think I make this point during my talk, and Professor Zhu also like emphasized this point. So I think like we can like leverage some like software like techniques to help protect or detect and mitigate some like a hardware level fault. For example, like two like examples is like anomaly detection on the software side to help detect this like a hardware fault, or we can use some like software, you know, diversity, like data diversity, to help, you know, like detect and mitigate some like a hardware fault. So I think they do have some interactions, and the software can help the hardware, and definitely that like the hardware can help the software. So I think it will be very interesting to, you know, use some like lightweight software scheme to help these reliabilities of the whole like system. Yeah, I think it's a good way to go. Yeah, that's my answer to these questions.
Thank you very much, Zishen. I think in such a great panel discussion, time really flies. We only have a few minutes left. So the one last question for each panelist is whether you guys have any questions towards each other. If so, now it's the perfect time to ask each other a question. So I'll give it a minute, see if you guys have any question towards each other. If not, I have a final question. I think I personally came from the industry. Dealing with reliability, it's a pain. So today we have discussion on this, even the circuit level from Professor Metra, system level from Zishen, and software and algorithm level from Yuhao, and industry perspective from Dr. Yu. Do you guys see a unified model to model the cross-stack reliability measure, whether the system is reliable enough or not? So what's your take on this question, a cross-layer theoretical model to model the whole system's reliability? Professor Metra, since you are the most senior expert in the field, I think you have the authority to answer this question.
I was thinking, so that's a very good question, and a big problem. I think it's still a concern. So typically we have goals at the system level, but then to satisfy, I think you need to go down at the components level, as I was also somehow trying to mention. And so that would be very good. I think it would be also an issue for standards. So maybe try to agree and standardize, let's say, some metrics that could help moving from the system level down, or to be sure that what we have at the system level is accurate, as it could be at lower levels. Because basically the problem is accuracy, you know? So in the sense of your estimation. So you may use any abstraction level also in testing or whatever, but if you deal with physical faults, they happen at the physical level. So the higher you move in modeling the effect of these physical defects and so on, you risk to make mistakes. So probably it's really an issue that should be addressed, as also based on your previous question, together with the not only academic but industry especially, and so on, and try to define some metrics that could work well, and let's say help moving from the system level down to the circuit level and back without losing any accuracy, so that we are sure that what is predicted is actually describing the reality and likely making us safe enough for these machines. But that's a big issue.
Thank you so much, Professor Metra. All right, to conclude, we hope through this talk, we all gain some insight regarding reliability problems in autonomous machines. I certainly have learned a lot, and I learned to thank the organizers, Sorel, Carmen, Steve. Especially I want to thank the speakers as well, Professor Metra, Professor Zhu, Dr. Yu, and Zishen. And thank you very much. And then hopefully the audience can enjoy this panel.
Thank you all.
Thank you.
Thank you all
very much for participating.